Assalamu alaikum warahmatullahi wabarakatuh and very good morning, all of you. On behalf of Center for Postgraduate Studies, International Islamic University, Malaysia, in collaboration with Postgraduate Student Society of Kuantan Campus, I would like to warmly welcome everybody to today's postgraduate workshop on multiple linear regression analysis. Thank you all for joining online today via Zoom this morning. We are delighted to see a lot of postgraduate students and researchers from various disciplines coming together to enhance their statistical and research skills today with us. This workshop is scheduled from 10 a.m. to 12 p.m. and we kindly ask all participants to mute their mics throughout the session, and you may post your questions in the chat during the Q&A session later. So it's a great pleasure for me to introduce our distinguished speaker for today, Dr. Noor Ain Binti Mahat. Dr. Noor Ain holds a Bachelor of Nursing Honors, a Master of Epidemiology and Medical Statistics, and a PhD in Science and Technology. She is currently the head of the Department of Professional Nursing Studies, Kuliah of Nursing, IIUM, and also serves as the Statistical Clinic Consultant at Kuliah of Nursing at IIUM. And without further ado, I would like to invite Dr. Noor Ain Binti Mahat to begin her session. Dr. Noor Ain, the floor is yours.
Assalamualaikum and very good morning to all of you. I hope you can hear my voice clearly.
Yes, Dr. Ain.
All right, thank you so much. Let me share. Wait, Okay, so without further ado, I would like to thank CPS for inviting me to be the speaker. It's actually a sharing session on multiple linear regression analysis using Spss software. And at this level, this one is at postgraduate workshop, right? At postgraduate studies. So basically, everyone would like to refresh their knowledge on statistics because it's very much related to data analysis. It's part of the thesis production that you need to produce at the end of the school years, at the end of the master's or PhD years. Okay, so hopefully that today this workshop will meet your expectation in knowing or in advancing your knowledge on multiple linear regression. Okay, inshallah. Now, you can stop me at any time. I'm okay with it. If you post any questions in the chat box, hopefully that the organizer able to help me to tell me the questions, because I'm afraid that I'm not aware on the questions in the chat box. Okay. Okay, without further ado, let's start. I tried to accommodate this lecture within 2 hours. Okay, hopefully I can do that. All right. So this is the outlines of today's lecture. Not really a lecture lah. Today's sharing on the multiple linear regression. So we start off with this simple linear regression. Okay, simple linear regression. And then multiple linear regression, step in handling MLR, okay, MLR, or we call it as multiple linear regression or MLR. And today we will cover on how to present and how to interpret the analysis, the MLR, okay? Now, if you have two variables, okay, if you have two variables, like for example, you have a mother's weight at first antenatal checkup. Antenatal checkup is ANC. So this is measured in kg. Okay, mother's weight in kg, and you have the weight of the birth weight of the newborn, also measured in kg. So if you have these two numerical variable, okay, you want to see if Are these variables associated? Are these variable related? Okay, is there any significant association or relationship between these two variables? Okay, so what test can be done? Okay, what statistical tests can be done or should be used to determine if there is any association between the two numerical variables? So basically, we have at this level, right? We have different types of variable. The main thing is one is categorical variable, another one is numerical variable. So I would like to emphasize this in all of my lectures, in all of my sharing. You need to know what types of variable of your data, of your variable. It's either categorical or numerical. Okay. So categorical means your variable is in categories form. For example, gender. We have male and female. Okay. And if it is numerical, means it is measured in numbers or figures. Okay, for example, the age of the participants or the weight, the height, the BMI. So that is numerical. So if you have these two types of numerical variable and you want to measure the association, what do you think is the test, the statistical test that can be done? Anyone who would like to try?
Pearson correlation.
Correlation, excellent. Okay, Pearson correlation, very good. All right. So you can perform either correlation or regression. So both can give you significant association, can give you the data or the p-value to determine whether is there any relationship or association between these two variables. But the difference is in correlation, it gives you the R value, which is the strength of the association. However, in the regression, it gives us the regression equation, which gives us more detail, all right, y equal to a plus bx, all right, more details interpretation of x and y, all right. So that's good, very good. Now, okay, a quick revision lah on the simple linear regression. This used when you want to determine the association of two numerical variables. It must be numerical, independent, and dependent variable, right? Independent is the risk factor or the factors, and dependent is the outcome, all right? So basically, in simple linear regression, it gives us the best fitted straight line, okay? The best fitted straight line, the method of least square. So, okay, this is the method of least square, all right? If let's say, what is method of least square? Method of least square is to find the best fitted line, okay? That minimize the sum of squared differences or residuals or errors, all right? Minimize means the smallest value of sum of squared of differences. Differences of what? Differences of our data. This is observed data, okay, observed value, all right, observed value. So SPSS will give us the best fitted line with the minimum differences, quite sum of squared. This is the differences. We call this as the differences, or some reference call them as residuals, or some call this as errors. Okay, differences, residuals, or errors, all right? So SPSS will give us what is the best fitted line. So if you compare the blue lines above here, okay, the blue line, definitely it's gonna have a much higher errors, okay, as compared to the best fitted line here, okay, with smallest errors, okay. So error is actually observed minus the predicted. So this is the observed, our data is observed, and this is the predicted, okay, predicted line, okay. Just to familiar yourself in simple linear regression or multiple linear regression, it's very common for us to know the term of errors or residuals are very common when you search or read for the articles for the reference on the SLR or MLR. Okay. Okay, for simple linear regression, at the end, it will give us the regression equation of y equal to a plus bx, all right? Y equal to a plus bx. So what is y? Y is the dependent variable, okay? A is the y-intercept when the value of x is 0, okay? So the intercept here is the value of a, and B is the slope, okay? The slope, right? The slope. What does it mean? It gives the rate of change in Y, okay, for any 1 unit increase in X, meaning to say that in 1 unit increase in X or decrease in X will increase or decrease by how many minutes, by how many units, okay? That is the slope that give us the value of how many unit it will change, yeah? And x is the independent variable, right? So y equal to a plus bx, okay? Actually, this is the scatter plot, okay? The scatter plot of two numerical variable of x and y. All right, again, from the equation, we managed to know the change, the rate of change of x, okay, based on the b, okay, based on the slope given. 1 unit increase in x increase by how many units? Okay, in this case, it is increase, right? Increase. But if the graph is like this, it's going to be inversely proportionate, right? Inversely proportionate. Yeah. Now, I would like you to download a dataset named SGA dataset. All right. You can just type in this URL, this link. Just type this link of tinyurl.com/SGA trial, because we are going to use that data set throughout this workshop. Okay, I gave you time for you to download. Okay, can you tell me if you managed to download the data set? Okay, this data set on SGA. Okay, Shahu, are you able to download the data set?
Yes, doctor.
Okay,
Amen.
very good. Now, can we proceed?
Yes.
Okay. Now, how to do simple linear regression? This is the steps. that you can refer to on how to analyze your data using simple linear regression. Just click on the Analyze, Regression, and Linear. All right. So can we do it together? Let me show you. If you don't have any laptop with you, you can just observe first. Okay, see it first, and you can try it out later on your own. Okay. All right. Okay, you can go to Analyze, Regression, Linear. All right. Reset. Let me reset first. Okay, our dependent just now is the birth weight. Okay, the birth weight. Let's search for the birth weight. Here is our birth weight. And the independent variable just now was weight at first ANC antenatal checkup. Okay, weight at first ANC. So next is you click on the statistics box, okay, and then click on the confidence interval, and the rest just leave it by default. Continue, and then click OK. Okay. So this is the table of coefficient. All right, table of coefficient here. As you can see, the constant is the y-intercept. Okay, the constant is the value of y-intercept, which is 1.662. And the slope is beta value, okay, for weight at first ANC, which is 0.021. Okay, let's go back to the slides because I think I have that in the slide. Okay. All right. Now, how to interpret this? Okay. This is the y-intercept. Okay, 1.583. Okay, it was different from just now. It's okay. And then this is the slope, 0.022, and this is the p-value. The SIG is the p-value, 0.000. Okay, I would like to tell you here that if you find any p-value of 0.000, please don't write it as 0.000, because if you double-click the SPSS output just now, it will give you a very small values of 0.0000025, for example. So that's why it shows you here 0.000. So for any reporting in chapter 4 in the results section, so make sure that you put as p less than 0.001. Okay, don't put 0.000. All right. Okay. P less than 0.001. And this is the confidence interval. So when you substitute the value in the equation, it's going to be y. Y is the birth weight, our outcome, equal to A, 1.58. Okay, 1.58 plus 0.02. Okay, 0.022 from here. And X is the mother's weight at first antenatal checkup. So how to interpret? 1 unit increase, 1 kg increase of mother's weight increases birth weight. Why is it increase and why it is not decrease? Is because the positive value here, positive 0.02. Okay, positive 0.02. Increase the birth weight by 0.02 kg. Okay. Also, if you want to interpret per 10 kg, for example, you can just state that an increase of 10 kg of mother's weight increases birth weight by, we need to move the decimal point, decimal point become 0.2 kg instead of 0.02 kg. Okay, either one. All right. If you want to interpret by per kg, 1 kg also can. If you want to interpret by 10 kg, because you said that 10 kg is more meaningful as compared to 1 kg, it's okay. You can do that. So it's going to be increased of 10 kg of mother's weight, increased birth weight by 0.2 kg. All right. Now, let's move on to multiple linear regression. So we have revised back on the simple linear regression on the SLR. Now, let's focus on the multiple linear regression, our main agenda here. For any analysis, for any association, for any relationship, in real life, right? In reality, it's impossible for us to determine the association of only one variable towards one outcome, all right? Because in reality, in any diseases, for example, or any condition, there are multiple factors that cause or associated with the outcome, all right? It's not only a single factor, it's multifactorial, multiple factors. So because of that, we propose multiple linear regression because in multiple linear regression, we can have more than one independent variables or independent factors. Okay, more than one factors. In order for you to proceed with MLR, you need to make sure that dependent is numerical. Okay, it must be numerical. And what about the independent? The independent, logically, right? If you think of simple linear regression, yes, you need numerical variable. However, you can also include categorical variable in the independent factors. Some reference stated that when you include the categorical variable, they have a special name for that association or for that analysis. It is going to be the general linear regression. Okay, general linear regression. But some they just mentioned on the MLR. Okay, they call them as multiple linear regression with categorical independent variable. Okay, so at this moment, okay, bear in mind that in order for you to proceed with MLR, the dependent must be numerical and the independent must be numerical. It can be numerical and categorical variable. All right, let's look at the example. You want to determine what are the factors associated with the birth weight of the newborn. All right. And you found out from your literature, you found out that these 4 factors were associated with the birth weight, all right? The mother's weight during the first antenatal checkup, the age of the mothers, the smoking status, as well as the parity. How many children does the mothers had before? Okay. All right. So our example or our analysis is based on this scenario, yeah, on the birth weight and the factors including mother's weight, the age, the smoking, as well as the parity. Determine the associated factors, the influencing factors, or the risk factors, or you want to develop the prediction model, right? Now, these are the steps in handling multiple linear regression. Step number 1 is to run the simple linear regression first. Okay, to run simple linear regression. All right, and then step 2, variable selection, and the rest of it. It will go one by one. So as for now, let's run the simple linear regression first. All right. Why do we need to check for the simple linear regression? It's because we want to know the crude relationship of individual independent variable respectively, all right? The respective independent variable, all right? Because later we will compare it with the results of multiple linear regression, and from there we know the possibility of the presence of confounding factors before and after. For example, before it shows significant results, all right? Before means in simple linear regression shows significant results, and then later in the multiple linear regression, it become non-significant, for example. So we know that there is a confounding factors happened, okay, during the, to reduce, to limit the bias, to limit the confounders during the analysis, okay? And another reason is for variable selection. All right, for your information, in a larger scale study, with thousands of independent variables or predictors. Okay, there's going to be a lot of predictors that the researchers have in a big scale study. So in that case, we need to really select a significant or mostly significant, a significant results or significant variables to be included in the multiple linear regression. So that's why we screen them during simple linear regression before we can select them for the MLR later on. Okay. Okay, you have learned, we've touched on the simple linear regression. Now, what if the independent variable is categorical variable? For example, smoking status, okay, with two categories, smokers and non-smokers. Okay, how to do about it? All right. Now, if you have a categorical independent variable, for example, smoking status, okay, please bear in mind that in MLR, we can analyze for dichotomous variables only. Okay, dichotomous means with two categories. Two categories, for example, gender, male, female, disease status, yes, no, hypertension, yes, no, and so on, right? It should be coded as 0 and 1. Okay, 0 and 1. So in any categorical variables, remember that we need to give values to them. Okay, so we need to give 0 and 1 because, all right, usually we will compare the two groups. Okay, usually those who are coded with 1 is compared against the reference group or those with 0 code, okay, with the code 0. All right, it's for comparison, easy comparison. So usually we will compare those coded as 1 against those with 0. Okay. All right. So it's going to be like this. All right. So this is inversely proportionate. Okay, inversely proportionate. As you can see, the line is going down. Okay, so a unit increase in between the two groups, 0 and 1, smokers against the non-smokers. So what is the gradient here? The B, okay, the B. What is the gradient for us to interpret? Okay, let's look at the example later. Now, what about the categories of more than 2 levels or more than 2 categories? For example, education level, we have no education, no formal education. We have primary education, secondary, and tertiary educations. Here we have 4 categories, all right? 4 categories. How to analyze this? Okay. What you need to do is you need to create dummy variables. Okay, dummy variables. What is dummy variables? Basically, we separate. In other words, we separate the categories into several variables. Okay, for example, in this case, we have 4 levels or 4 categories with no education, primary, secondary, and tertiary. So the number of dummy variables is going to be 3. Why 3? It is k minus 1. K means how many categories do we have? Minus 1. So we have 4 categories from the above here, education level. Okay. 4 minus 1 is 3. So how to do that is, basically, we need to split the education from one variable just now. Okay, from only one variable become now 3. Education, or edu1, edu2, and edu3. Okay, how to do it is, remember that we have the original of no education, primary, secondary, and tertiary. We need to find what is the reference group. Okay, first of all, we need to find what is the reference group. How to select the reference group? Usually the reference group is those with less risk, okay? Or if you don't know about it, you can look at the proportion of the outcome in between the level of education, which level has the least proportion of the outcome. So that can be the reference group, okay? The low risk and things like that, right? So in this case, I would like to have no education as the reference group, okay? So in Edu1, meaning you are comparing primary against the no education, okay? Primary against no education. So in primary, it should be coded as 1, and the rest becomes 0, okay? No education 0, and the rest as well becomes 0, secondary and tertiary. For Edu2, you would like to compare secondary education against no education. So secondary become 1 and the rest become 0. Okay? And Edu3, okay, Edu3, you want to compare tertiary education against no education, and the rest become 0. Okay, so this is the concept of dummy variables if you have more than 2 levels of categories. Why do we do this? It's because for MLR, okay, for multiple linear regression, this is needed if you have categorical of more than 2 levels or 2 categories. So we need to split. Basically, the main concept is to split the variable into different or more variables. We, first of all, make sure we know which one is the reference group that we want to compare with, and we will compare each of the rest of the categories towards the no education. Okay. So how to do this is, okay, you can transform, okay, use function transform, recode into different variable, okay, right? Transform, recode into different variable, like in this case, okay, and then you click the name of the variable, the new name of the variable, and then change and old and new values, okay? Let me show you. Okay. All right. Okay, we go to, this is our data set. All right. Data view, you can just do in any data view or variable view. All right. So we go to transform. recode into different variable. Okay, we have education level. Now we would like to develop or create edu1. Edu1 change. Okay, already edu1 change, and then click on all and new values. All right, so just now, originally, you need to make sure what values were given to each of the categories, okay? We want to compare in edu1 the primary against the reference group of no formal education. So, let me show you, yeah? The education, all right. 1 is nil, 2 primary, 3 secondary, 4 is tertiary. So if you want to create edu1, the 2 will become 1, okay, and the rest will become 0, okay? Let's go back again, recode into different variable, education level, edu1, change, click on all and new values. Value number 2 become number 1. And you can just click one by one, like 0, 0, 3, 0. But the quickest way is you can just click on the all other values, become 0. Okay, else means, remember we have 4 just now, no formal education, primary, secondary, and tertiary. So we set already the primary into 1, okay? And then the rest means those without formal education, secondary, and tertiary become 0, all right? So that is the meaning of else equal to 0. Continue, okay. All right, so let's look at our data. All right, so we have newly developed variable of edu1. Okay, edu1. Okay. And you can do the rest for edu2 and edu3. Okay. All right. Any questions so far? For simple linear regression?
Salam Doktor, there
Yes,
is a questions at the chat box. Salam Doktor, how do we interpret dummy variable in result if one of them is significant?
Okay. How do we, all right, let me see. I think whether I don't have the example for that. It's okay. Good job. All right. Now, how to interpret if it is significant? So basically, remember that we have created dummy variables, all right, from one variable of education level into 3, okay, into 3, edu1, edu2, and edu3. So in the results, we will put here edu1, edu2, edu3. Okay. All right. So there will be a value here as well as the p-value here. Okay. So you might have only one that is significant. If let's say here 0.03 and the rest are not significant. Okay. So from these results, how you can interpret is, remember that, okay, wait now. Okay. Okay, I did not put the interpretation. Okay, no problem. Okay, remember just now that we are comparing only the two categories. Like in Edu 3, it's in between tertiary versus the no formal education. Okay, no formal education. So how can you interpret is, let's look at the beta. Okay, the beta, for example, here is 0.03. Okay, because our dependent variable is the birth weight, birth weight, it's in kg, all right, it's in kg. So how can you interpret is, mothers with tertiary educations are statistically significant, okay, has higher increase of birth weight by 0.03 kg as compared to mothers without no formal education. All right. So in the results, there is no more education level. But replaced it with Edu 1, Edu 2, and Edu 3. Or you can put Edu 1 in bracket, primary versus no education. This one is secondary versus no education, and this one tertiary versus no education. So this will show a clear interpretation, okay? And the readers would know that, oh, you already split up the education level, okay? Remember, this one is for analysis, right? But in your earlier results, okay, you will explained about the socio-demographic characteristics, the descriptive statistics of the socio-demographic characteristics. In that table, you still need to present your education level. Okay, your education level, which consists of no education, primary, secondary, and tertiary education. This one is socio-demographic characteristics. The frequency, the percentage, the descriptive statistics during earlier introductory results, earlier chapter 4, earlier results, you need to present this one. This one is only for the analysis, okay? For the analysis, the dummy variables, okay? And the 1, 2, and 3. I hope this answers your question. All right, you're welcome. Let's proceed. Okay, is there any minimum response for categorical data? Is there any minimum response? Wait, let me see. Is there any minimum response for categorical data? Example, smoking status. No, there is no minimum response or requirement needed for categorical variable. You can just proceed, Hafiza. Okay. All right. So I believe that you can do this on your own, yeah, on the simple linear regression. You're most welcome. Okay, this one is the results. You can just compare with this results, yeah. Now, next is variable selection. Okay, what is variable selection? Variable selection. All right. Now, what is variable selection? Variable selection is when you want to choose variables in the included model and include it in the model, okay, by removing those who are not relevant, irrelevant. So how to choose the variables to be included in the final model, because a set of variables that provide the best fit, okay, so that accurate prediction can be made. So we don't want any irrelevant variables to be included in the model. Okay, model. We're talking about model is because the equation itself is the model. Okay, the final included variables in the equation is the model. Okay, the final model. So model itulah modelnya. Hopefully you are familiar with it. The model is the regression equation that you will get later on at the end of the analysis. So I have given you this link of paper that I would like you to read on. Okay, it's a good paper. It's about wait, okay, variable selection strategies, and it's important in clinical prediction model. Okay, here thoroughly explained. I like this article because it explained about the basic principles of variable selection, and then how to do variable selection. And it even explained what happened during backward elimination, during forward selection, and stepwise selection. Okay, you can just go through this article later. As of now, okay, how to do variable selection? Select candidate variables. Select variable for the model. How? First, from the literature search. Okay, that's why you start with the introduction in your thesis, right? And then followed by literature review. Okay, if one of the objective is to determine predictors or factors associated with outcome. So in the literature review, you must have that. What are the factors or the predictors or the variables that are associated with outcome? All right. So in the literature, it says that here are the variables or the factors that associated with it. So you can include that variables based on the literature search. Next is based on the content expert. All right, you have your supervisor, you have your field supervisor, you have content expert saying that, oh, you must include this variable is because this currently showed clinically associated with outcome, for example. So you can include that based on content expert. Another one is if the simple linear regression, okay, if in the bivariate or univariate analysis showing that the p-value of less than 0.25 in the univariate analysis, okay, you do simple linear regression and the p-value is less than 0.25, you can include that in your model, okay? You can select that into your multiple linear regression, okay, in the variable selection, right? So all of these are how you can check for the variable selection. And then apply variable selection method to include in the final model. So there are several types of variable selection. We have backward elimination, we have forward selection, we have stepwise selection. Okay, so how to do this is actually you need to do all of these variable selection like backward, forward, and stepwise, and you will select only one method of selection with the highest number of variables that are significant. Okay, you need to do all of this and then select the method with highest significant results included in the model, right? If it is the same for all, usually I like to use stepwise selection lah. Okay, because it's the combination of backward and forward selection. Okay, backward means this is the simple words. Backward, what happened in backward is the Spss will include all of the predictors, all of the independent variables, and then it will remove one variable at a time. Remove one by one by one by one to get the best model. Okay, the best model. So forward is the Spss will include from nothing, okay, from zero, they will include one by one, and then include in the model, include to see the final effect, the final effect. Stepwise is the combination of backward and forward. In the process of getting that final effect, it can be backward, it can be forward in between, and then backward again, forward again. So that's why I like to, if let's say all of these method give you the same results of number, how many number of independent that are significant, then you can just use stepwise selection. Okay. All right. Next, all right, how to do this is I give you the steps. You can just follow later. Analyze, regression, the same thing, but what the difference is in the independent here. This is the independent variable, and this is the method that I'm talking about. Okay, we have forward, stepwise, backward, enter. Okay, enter. We can just choose accordingly, and then click on the statistics. By default, it clicked on the estimates and model fit. Just click on the confidence interval. Okay. All right. Okay, let me show you how to do this. Okay, analyze, regression, linear, weight at first ANC, and we have age of the mother just now. We have 4 predictors, 4 independent variables, predictors. And then we have smoking. One more is parity. Where is parity? Okay, here is parity. All right. So we have enter stepwise, remove Noah, backward or forward. Okay, so let's try stepwise. Okay, confidence interval checked. Anything else? Nothing. Click OK. All right. So this is the results. Okay. As you can see here, the model is model 1, model 2. Okay, in the model summary table. Okay, we have model 1 and model 2. Okay. Next is coefficient table. Okay, we have model 1 and model 2. All right. So please look at the recent model, which is model 2. Okay. In other analysis, you might have up until 4, 5, 6 models. Okay. Choose the most recent one, which is the lowest one lah. Huh? Not the lowest, the recent one. This number 1, this number 2. So number 2 is the recent one lah, the update, the recent. Okay, the recent. Okay. Now, how to interpret? Let's go. Not really interpret, no chat, no chat. Okay. Now, what we can see from the results, okay, from the results, this is a model summary. Okay, look at the recent one, number 2. Okay, model number 2. This is the, let's look at the adjusted R square. Okay, adjusted R square. Adjusted R square is equal to 0.216. Okay, 0.216. What does it mean? It means that 21.6%, make it percentage, move the decimal point, so it becomes 21.6% of birth weight is explained or predicted by the independent variables. Okay, the independent variables, like for example, mother's weight and smoking lah in this scenario, yeah, in this case. So it means that this model only predicted or explained by the independent variables or by the predictors by 21.6%. Okay. So what does it mean? All right. To be honest, right? If you do human studies, population study or human study, it's very difficult to get a higher value of adjusted R squared. Because like this 21.6% explained by the predictors that you include in the model, in the analysis, and the rest of 79% explained by the other factors that are not included in the analysis. Okay. Because human behaviors, human study is influenced by lots of variables like the behavior, the attitude, and so on. So it's not direct effect, or there's not a direct association between one factor, between a factor and the dependent variable. So if you've got about 50%, 60%, it's good enough already. Okay. Okay. All right, so the p-value here is p less than 0.001. It means that there is significant association between birth weight with mother's weight and smoking as a whole. The model as a whole is significant, okay? Next is the equation, okay, the model. Okay, let's look at the equation table, all right? Model number 2, okay? So we need to identify the values according to regression coefficient. Okay, birth weight, remember, based on this equation of y equal to a plus bx, let's substitute the value into it. Birth weight is our y, the birth weight, our outcome. Birth weight equal to 1.782. Okay, constant is the y-intercept. Okay, alpha A, 1.782 plus 0.021. Why is it plus? Because the value here is positive. This is the slope, the beta. Okay, the slope that we will predict the y based on x. 0.021, mother's weight, because the variable x is mother's weight, minus 0.196. Why is it minus? It's because negative sign here. Minus 0.190. X is the smoking because it belongs to smoking, right? So this is the preliminary main effect model. Okay, the preliminary effect model, right? So we know that a unit increase in mother's 1 kg increase in mother's weight will increase birth weight by 0.021 kg. In the smoking, those mothers who are smokers, okay, remember that we compare smokers against the non-smokers because 1 is smokers and 0 non-smokers. Okay, so smokers, those mothers with who are smokers tend to have a lower birth weight by 0.1 kg as compared to mothers who are non-smokers. Okay, smokers still reduce the weight by 0.19 kg. Okay, those who are smokers will tend to have a smaller baby lah, in other words, yeah. All right, any question before we go to step 3? All right, step 3, do you need to take a break? Can we proceed?
Yes, Doctor.
Yes.
Yes, Doctor, please.
Yes to proceed, eh? Okay. Oh, 11 already. Okay. Step 3, okay. Checking for interaction and multicollinearity. All right, we have our preliminary main effect model, and then we need to check for the interaction and multicollinearity. Now, what is interaction? All right. Okay, interaction is when you see, okay, interaction is when the effect of pet variables or pet effect variables differ from the individual effect. Okay, the individual effect. So basically in interaction, you will check for the two-way interaction of each independent variables or of each predictors. You will check one by one. So the pair, okay, the pair is what we call as interaction, interaction between the pair. For example, we have the weight of mother, smoking, age, and one more is parity. Okay, so you need to pair all possible combination in between the independent variables or the predictors, right? So for example, you need to pair the weight with smoking, weight with age, weight with parity, smoking with age, smoking with parity, age with parity. This is the most possible pair that you can get based on the number of predictors. Okay. Now, how to create the interaction is by using transform, okay, and compute. All right. And then what you need to do is you add the interaction into the model using enter. Remember just now there is enter function, variable selection of enter, and then see if the interaction is significant or not. Okay. If the interaction is significant, where it is less than 0.05, it means that there is an interaction between the two variables, right? So you need to check one by one interaction term at a time. Okay, one interaction term at a time. So if it is significant, okay, if the interaction shows significant results or p less than 0.05, therefore it means that there is an interaction between the variables. You need to add the interaction term in the final model, become a new variable of interaction. Okay. How to create the interaction term, transform, compute variable, all right? And then we use the icon times star ni. Okay, star times. This is the first variable, this is the second variable, right? Star means times. Interaction term means you times the two variables. Like in this case, if you look at the data set, for participants number 1, the weight 73, smoking is number 1 because she's smokers, she's smoking. So the interaction term become a value of of the interaction, which we times it, both of it, right? Become a value, right? That's the concept of interaction term. And then after you create the interaction term here, you need to include in the independent variables and then make sure the method is in enter and then click OK. All right, so it gives you the results of 0.368. Okay, 0.368. More than 0.05, therefore, we do not reject the null hypothesis. There is no interaction term. Okay, there is no interaction between weight and smoking. Okay, no interaction between weight and smoking. Therefore, we don't need to add the interaction term in the final model. Okay. All right. So let's do interaction term. Okay, transform, compute variable. Okay, compute variable. Okay, compute variable. And then the interaction is in between smoking. Contohnya, for example, smoking and age. Okay, smoking. Where is our smoking? Smoking. Okay, smoking times the age. Okay. Alright, okay. And then go back to our analyze, regression, linear. Okay, our dependent just now was birth weight. Birth weight is the dependent. The age of the mothers is independent. Weight at first ANC independent. Smoking independent. One more is parity. Parity. Okay. Now we need to add one more, which is the interaction between smoking and age. Method enter. Click on the confidence interval and then click OK. So let's look at the interaction here. Smoking and age, the p-value is 0.347. Okay, 0.347. It means that there is no interaction between smoking and age. Okay. All right. Next, moving on to multicollinearity. Okay, what is multicollinearity? It means that when the independent variables are highly correlated, okay, are highly correlated with each other. Okay, we don't want that to happen because if multicollinearity is present, means our model is not stable. Okay, the model can be exaggerated or over or undervalue. Okay, the effect is over or undervalue lah. What is the effect here? Larger p-value, so it become not significant, not statistically significant because p is more than 0.05, and the appropriate variable might be rejected wrongly. Okay, so in multicollinearity or MC, we are checking the VIF, okay, variance inflation factor. Okay, so how to check for the VIF? Okay, the same step as before in MLR, where you need to only check the collinearity diagnostic. Okay, check the collinearity diagnostic to see what is the value for VIF. Okay, VIF. Okay, let's see. Analyze just now, regression, linear. Okay, we need to 1, 2, 3, 4. Okay. Statistics, check on the collinearity diagnostic, continue, and okay. All right. So as you can see here under table, Okay, under table, coefficient table, all right, coefficient table, collinearity statistics of VIF. For model 2, weight at first ANC is 1.001, smoking is 1.001. So how to interpret this is, after checking, what's next? So make sure that it is less than 10. Okay? Make sure the VIF is less than 10. All right? If it is more than 10, okay, more than 10 means you have multicollinearity between the independent variables or the predictors. Okay, you have multicollinearity. So something need to be done. All right. So all right. So logically, right? Logically, why do you have higher why do you have multicollinearity or MC, or why do you have higher VIF? It's because all the predictors are correlated. Okay, so how can you reduce it? Is you need to remove what is really correlated. You need to remove the variables because it shows that there are two variables or more that are measuring the same thing, okay, and become your predictor. So how to solve that? The easiest way is just remove the predictors, yeah, because they might assessing the same component or the same things in the study, okay? All right. So we have run the simple linear regression, okay? We do variable selection. We have checked the interaction as well as the multicollinearity. Next, we need to check for the model assumptions and outlier. Okay, model assumption and outlier. How to check for the assumptions and outlier? Okay, yeah. All right. Okay, so this is the assumptions of multiple linear regression. The first one is random sample. Okay, it must be random sample. It can be either simple random sampling, or this one is at the planning stage, okay, data collection stage, okay, where how do you perform your data collection? How do you select your participants? It must be a random sample, either simple random sampling or stratified sampling or systematic random sampling or cluster sampling. Okay, next is linearity. Okay, linearity. Linearity, we will check. Check for what? Okay, we are checking for the errors or the residuals plot. Okay, remember for model assumption, it is based on the residuals or the errors or the difference. Remember the difference or the residuals or the errors is the difference between observed and the predicted value of the dependent variable. Okay, of the dependent variable. So we need to have the residuals or the errors of the dependent variable. So how to get that? We will look at it later, but it actually the difference between observed and predicted value. Now, we will check for the linearity of the overall model fitness, okay, the overall as well as of each independent variable, okay, of each independent numerical variable, right? So this is linearity. Next is we will check for the normality, okay, the normal distribution of the residuals of the error. And then we will check for the equal variance, okay, equal variance of the error or the residuals. Yeah, everything here is about the residuals or the errors, okay, in MLR. Now, how to calculate for the residuals at the same MLR, linear regression just now, okay, the same page or the steps, we need to click on the predicted values, okay, unstandardized predicted values as well as unstandardized residuals, okay, predicted values and unstandardized residuals or the errors, residuals, okay, all right. Now, let us go to our SPSS, how to get the predicted as well as the residuals. We go to analyze again, regression and linear, okay. Click on the, options, save. Okay, click on the save. And then under predicted value, you click on the standardized. For residuals, you click on the and standardize. So we're going to have the predicted value as well as the residuals. Click continue. Click OK. Right? Okay, if you can see down here, we have two new values of predicted and residuals. Okay, predicted and residuals. All right, let's look at the data view. Okay, so this is our predicted and residuals. Okay, this is predicted and this is residuals. Now, okay, let's look at the example. Okay, one data lah, one participants. All right. So this is our model just now from the results. Okay, from the results, this is our model, birth weight. Okay, our equation model, birth weight equal to 1.782 plus 0.021, mother's weight minus 0.160, smoking. Okay. So let's substitute. Okay, how to get the predicted. Okay, this is the steps behind of getting the predicted and the residuals. How to get the predicted is we substitute the number in the equation. Right? Let's look at the one example. The respondent of weight, the mothers are 73 kg, smoking. All right. So just substitute in the equation, birth weight of predicted equal to 1.782 plus 0.021. And the mother's weight for the first participant is 73 minus in the equation of 0.19. In bracket for smoking, it is 1, okay, for the first respondent. And after you calculate, you will get predicted of 3.12. Okay, 3.12. This is how to get what is the meaning of predicted, okay? When they substitute the information of the respective individuals or participants in the equation, okay, to get the predicted. Now, what about the residuals? Okay, I mentioned just now, it's the difference between observed and the predicted. And our observed value is what we get from our study, which is the birth weight of that mother's newborn is 2.17. Okay, minus the predicted 3.12, and you will get negative 0.95. See? Okay. This is the reason behind of this analysis of getting the value of predicted and residuals. Okay. All right. Now, after we have our predicted value and we have our residual value, now we can check for the assumptions of the model. All right. Random sample cannot be checked because this is already being done, okay, at the study design phase, at the design phase. So we exclude this in the checking for the model assumption. And then for the linearity, okay, linearity of the overall model fitness, how to check is from scatter plot. Okay, from scatter plot, okay, between residuals and the predicted value. Okay, same goes to equal variance. Okay, this one. Same goes to equal variance. How to check is the same thing of scatter plot between residuals and predicted. Normality of residuals, how to check is by doing histogram. Okay? Histogram of the residuals and linearity of each independent variables. How to check is by doing scatter plot between residuals and each numerical variable. We don't check scatter plot for categorical variable, all right? Meaning to say that if your predictors have categorical variable, we don't check for the linearity of each of the categorical variable. We don't do that, yeah? We do the scatter plot for numerical variable only. Okay, now the first one. On the scatter plot, okay, overall linearity of the model. Okay, overall linearity of the model. So how to do scatter plot? Okay, how to do scatter plot? So please bear in mind that X is the predicted value and Y is the residuals. Okay, X is the predicted value and Y is the residuals. Let's go to the data set. Okay, how to do scatter plot? We go to graph, legacy dialog, and scatter plot. Simple scatter, define, and please fill up the X and the Y. Okay, as I mentioned just now, the X is the predicted. Okay, it's not moving. Okay. Predicted is X. No. Predicted. Okay. Is at X and our residuals is at Y axis. Okay. And then click OK. All right. So this is our scatter plot. Okay. This is our scatter plot where we have predicted values at X and we have residuals at Y. How to interpret this? Okay, how to interpret this? We need to make sure that this scatter plot shows a linear shape, okay? Linear form or linear shape. Linear means straight line, okay? If you can see here, it's going straight, okay, without any direction, right? Without any direction. If you find your linear assumption example, when linear assumption is not met, is like this, where you find direction with different shapes. Like for example, here it's S shape or U shape or like this. Okay, so make sure it's in linear form, straight line, right? Linear. This is overall linearity, yeah, overall linearity. As well as I mentioned in this table, okay, in this table, the scatter plot can be assessed, can assess the linearity for overall as well as the equal variance. Now, let's look at the equal variance. Now, the equal variance using the same scatter plot, what should we look at? Okay, so if you find your scatter plot in this shape, okay, it means that equal variance assumed, okay, is met. Equal variance is met. Like this, or this, okay? However, if there is any constant increasing or decreasing like this, like constant decreasing, constant increasing, so this shows that the equal variance assumption is not met. Okay, the equal variance assumption is not met. So make sure it has equal variance or symmetrical between right and left. Okay, between right and left. Next is to check for the normality of residuals. Okay, normality of residuals. How to check is by looking at the histogram. Okay, this histogram. Right? How to do histogram of the residuals, yeah? Remember histogram of the residuals? How to check for the histogram? Let's go to our data set. We go to graph, the legacy dialog, histogram. Okay. And please insert the residuals in the variables, and you can click on the display normal curve. Click OK. Right? So this is the histogram of the residuals. Remember, for checking assumption, we are checking on the residuals, right? Okay. If your histogram shows a symmetrical shape, okay, symmetrical shape, this is symmetry, then normal assumption is met, means it is normally distributed, normally distributed of residuals. Assumption is met. However, if your histogram shows right skewed, okay, skewed to the right or left skewed, it is not symmetry between right and left. Okay, when you draw the straight line here, it is symmetry in between right and left. Okay, so if it is skewed, means data assumption, normal distribution is not met. Okay. Okay, we have question. If we include, okay, we have question from Amirul. If I use convenience sampling, can I still run MLR? Okay. That's what happened in many cases. In many cases. All right. How to tell this? Theoretically, okay, theoretically, you need to perform random sampling. You need to perform random sampling. That's one of the requirement to do MLR. However, can I still do if I select my participants using convenience sampling? It's very difficult to answer this. Supposedly, you cannot use MLR. However, okay, I would say that if we met the central limit theorem, a central limit theorem's formula, which is if your sample is more than 30, in which I believe it is more than 30, especially if you are doing human studies or population studies, right? So it's gonna be more than 30, then it is okay to run the MLR. So that's why sample size calculation is very important to make sure that you have the minimum number of sample in order for you to conclude that there is a significant difference between the association. Because of that minimum required sample size that help to make sure that you have a significant results in the association. So the answer, if possible, please use random sampling. If you cannot, then you can still use MLR, okay? Provided that you have a sample of more than 30. Okay. Next question from Hafiza. If we include interaction term, do we need to remove the individual IV? Okay, Amirul. Okay, Amirul said his sample is 400. Yes, you can proceed with MLR. Okay. Going back to Nurul Hafiza, stated that do we need to remove individual IV in our regression model? For example, age, weight is significant. Do we need to remove age and weight in our equation? The very good questions. The answer is no. You don't need to remove the original variable, okay? Just add the new interaction term that is significant. Okay, please maintain the original model. The new addition is the significant interaction term only. Okay. All right, so this is okay, if you want to include the interaction term, please be very, very careful because logically, right, if you include the interaction term with existing original variable, for example, age and weight, okay, age and weight, but the model also already include age and weight, it may introduce multicollinearity because it's actually, even though it's interaction, but it's actually is the same variable. Okay, the difference is only the interaction. So please be careful on that. There is one more step that you need to do. Okay, I think better if you can confirm this with any statistician that you know. Okay, where you need to minus. Okay, this is another story lah on how to analyze that. So the interaction, before you do the interaction term, you need to minus the x, okay, the values with the mean, okay, x minus the mean, and then you do the interaction, then only you check for the multicollinearity because we don't want the multicollinearity to happen because of the interaction term that is significant. Basically, that's the main reason lah. Okay. Okay, Amirul, Brother Amirul said. Dr. Amirul, oh, okay. If one of the model assumption is violated, what to do to mitigate? Okay, good question as well. Okay, the model assumption, okay, the assumptions are not met. For example, the normality or the equal variance are not met. So basically what happened is we will do the transformation. Okay, we will transform the data. All right. There are many ways on how to transform the data, depends on the situation. All right. These are a few examples that I can give for you to transform your data. Okay. All right. Number one is we do log transformation, LOG, log. Log transformation means we log our data, logistic log transformation. Next is either you do square root of the transformation, square root of the data, especially if it is count data. Count data means a round number. For example, the outcome is how many patients visit in that hospital monthly. So it is round number or count data, 10, 11, 12%. So you can do that square root transformation. Next is you do standardization of z-score, okay, standardization of z-score. For example, the values of the variables too, you need to standardize it by how? X minus the mean divided by standard deviation, meaning to say that we standardized the value to make it more normal, to make it more, to have equal variance, for example. Or, apa lagi? Or you can, I forgot the term, but you can minus the mean with the data. So those are the example of how you can transform your data. So the main concept is if your assumption is not met, and one more is the outlier. Later, I will touch on the outlier, but that's why before we do any analysis, we need to explore our data first to make sure that there is no outlier. Okay, this one is very crucial, it's very important before we start even descriptive statistics pun, all right? Before we start even as simple as descriptive statistic, make sure our data is clean and we don't want to have any outlier, okay? Because the outlier can be due to human error. Maybe sometimes we, because human who are filling up the data, so there might be errors. So yeah, because of that, outlier can lead to not met of a model assumption as well, and many other things. So the main concept is if the assumption is not met, so we need to transform our data and then recheck again. And yeah, usually it's going to be met lah, all the assumptions lah. It's going to be good. Okay, how to interpret the interaction with dummy variable and okay, most welcome. How to interpret the interaction with dummy variable and how to interpret the dummy individually. Okay, I think I will answer Brother Zakaria later lah at the end of during interpretation. Okay, during interpretation. Please remind me again, yeah, if I'm not answering that question later. Okay. All right. Okay. This one is, let's proceed, yeah? Let's proceed. Normality of residuals. Normality of residuals. Next is checking linearity of each numerical independent variable, right? The same, okay, we do scatter plot, but this time around, it's with numerical independent variable, okay? So the residuals is at y and x is the weight at first NC, any numerical variable, okay, any numerical variable. It's linear, okay, linear. Next is checking for outlier, all right, checking for outlier. We need to check for the outlier using standardized residuals. Okay, standardized residuals. So basically, we need to standardize the residual in order for us to determine if there is any outlier or not. Okay. So X is the predicted, unstandardized predicted, and Y is the standardized residuals. Okay. Standardized residuals. All right. Okay, now let me show you. Analyze, regression, linear. Okay, the residuals, we want to standardize it. Okay, click on the standardized residuals, continue. Okay, right? Next is, let's check for the legacy dialog and scatter plot. Define The Y here is standardized. Okay. Standardize. Click OK. Okay. Okay. So this is the scatter plot. Okay, when we plot the unstandardized predicted with the standardized residuals. Okay, so how to determine this, how to interpret this is to make sure that our data is within +3 and -3 of standardized residuals. If it is fall above 3 or below than -3 means there is an outlier. So what to do? This shouldn't be happened because you already check for any outlier before starting any analysis, right? So if you don't do any exploration of your data, if you don't clean your data, this can happen. This might happen, the presence of outlier. Okay, the presence of outlier, but usually it won't lah, it won't. Okay, because we already screened our data before we start anything. Okay, before we start anything. Now, so if there is any, we need to make sure remove the outlier lah. Okay, remove the outlier. Okay, next, last one is data presentation and interpretation. Interpretation and presentation and interpret. Okay. Now, there are many ways on how to present your data. Okay, if you read the articles, some might present or separate the univariate or the simple linear regression above, and then below it is the multiple linear regression. But some, they put side by side like this, simple linear regression and multiple linear regression. But some, they just mentioned about the multiple linear regression without telling the simple linear regression. There are many other ways. So you can just choose one. And I would prefer this way, where we can see side by side the simple linear regression as well as the multiple linear regression. So this one is factors associated with the birth weight. Okay. Among study population using multiple linear regression, and you can include the variable selection. Here, for example, using stepwise method, for example, all right? So we have independent variable, okay, 1, 2, 3, 4, mother's weight, age, parity, and smoking. We have simple linear regression. This is the beta, okay, regression coefficient. 95% confidence interval. This is the p-value. Okay, the p-value. We have two significant associated factors, mother's weight and smoking. And this is multiple linear regression where we put the adjusted beta. Okay, we mentioned 1 is crude, 2 is adjusted. And why is it dash here is because in the final model, we only have two included variables or predictors, which are mother's weight and smoking. So this is the p-value. For prediction study, we need to include the final model. This one is you just substitute just substitute the numbers lah, based on the regression equation. Okay. All right. So how to interpret is this one is remember in chapter 4, after table, then there must be interpretation below it or above. Okay. All right. So there must be, even though you cannot say that, oh, I only mentioned in the table, so no need to mention in the paragraph. No, you still need to summarize or interpret the table. Okay, and make it in paragraph form lah, in thesis form. All right, so here there is a significant linear relationship between mother's weight and birth weight with P less than 0.001. Mother's weight with additional 10 kg have birth weight higher for 0.2 kg because we move the decimal point here as we interpret the 10 kg. Okay. Smoking. Okay, smokers have 0.19. Okay, 0.9. Lower is because of the negative sign as compared to non-smokers. Okay, with two significant variables, the model explained 21.6% of variation of birth weight based on the adjusted R square of 0.261. You need to mention here the R square. The model fits well, okay, because you have checked the assumption. So model assumptions are met. There is no interaction between independent variables and no multicollinearity problems. There is questions, there is question asking me whether do I need to put every results, because you have checked for the assumption, you check for the VIF, you check for the interaction term, multicollinearity. There are lots of table. Okay, there are lots of table that you need to put. So basically, I would suggest for the students to put all of the assumptions checking at the appendices, but not in the main result section. Is because it's going to be lots of them and may confuse the assessors. But some assessors, they don't really care about the process of getting the final model. But maybe assessors like me, I would like to see the whole process of it. Okay, I will refer back to the appendices and see whether the multicollinearities are really less than 10, for example, as mentioned in the results section and so on. Okay, so please put everything that you have done. Okay, you have checking the histogram just now, the scatter plot and all. So put everything in the appendices. So let's go back to the question by one of the participants, how to interpret the interaction with dummy variables and how to interpret the dummy individually. Okay. All right. So first is on the interaction. Now, if let's say just now, the interaction between age and smoking. Right? So you found out that this interaction term are significant. Okay? So you put in the final model and then you get the results. All right? The results can be not significant. Okay, the interaction is not significant or the interaction is significant. So if the interaction is not significant, it's okay lah. Just nothing. You just put nothing because here the interaction is not included in the simple linear regression. Remember? Okay, we don't check for the simple linear regression for the interaction term. So if the age and smoking, if this interaction term is significant, you need to add one more row on the age and smoking interaction, and P, let's say here, is significant, 0.03. Okay, so how to interpret this is, all right, you mentioned that the interaction term between age and smoking are statistically significant. all right, statistically significant. Therefore, in the final model, okay, you treat the new variable as the interaction term, means you need to mention both variables together in the interpretation. For example, the smoking here, we mentioned about the smoking only, but for the interaction term, the interaction between age and smoking give a significant association with the birth weight of the newborn, for example. All right. So you just mentioned the age, the interaction between age and smoking increase the birth weight or decrease the birth weight by how many? Based on the adjusted beta. Okay, that is on the interaction. For the dummy, okay, for the dummy just now, if let's say we look at the example of Edu1, Edu2, and Edu3. All right. So if only one of the dummy is significant, for example, only Edu3 0.02 is significant, the rest are not significant, you need to include all of the dummies in the final data presentation, okay, on the results table, because these are all together. Okay, these are all together, all right? So remember, if you chose the stepwise just now, if these two are not significant, then it won't give you the results, right? So in order to get the p-value of these two variables, you need to use method enter. Okay, variable selection enter. Just now, remember that we use stepwise method, right? So stepwise method. In stepwise method, only Edu3 produced significant results. In the table, okay, in the results table, you must include Edu1 and Edu2 as well. You must portray, you must show the Edu1 and Edu2 because it's part of education, level of education. However, how to get the values for adjusted B, for T, for p-value is by using enter. Then you can fill up these values for Edu1 and Edu2 in the multiple linear regression. Okay, am I answering your question? Okay. Any other questions from the floor?
Doctor,
Yes, yes.
can you simplify everything like maybe the simplest form of this MLR, this one, can you? So I can understand better.
Yeah. Can. Of course. All right. Let me show you. Okay, in summary. Okay, in summary. Okay, in your research, basically in your research, if you have an objective, if your objective is to determine factors associated with or determine the predictors of with outcome, for example, and the outcome is numerical variable, all right? Numerical variable. If it is count data means in round number that I mentioned just now, number of diseases, number of cases, for example. So that one you need to use Poisson regression, Poisson regression. But this MLR, multiple linear regression, if the outcome is numerical with decimal point, okay? Usually it's for decimal point. And you have several predictors or independent variables of numerical or categorical variable, then you can use multiple linear regression. Now, how to do multiple linear regression? First is you need to run the simple linear regression. All right, it depends. If it is categorical, then you cannot run the simple linear regression. Maybe it's gonna be a t-test or ANOVA. All right, if it's 2 group, then t-test. If it's 3 groups, then ANOVA. So this is the univariate or the bivariate analysis to determine the gross association between each variables. Okay, that's number one. Number two is to make sure that you only include those who are who have higher chance to be associated with outcome with p less than 0.25. All right, and then we proceed with the variable selection. Okay, variable selection with different method, variable selection method. We have stepwise, forward and backward and so on. So after we done that, we have our preliminary model. We have preliminary model. Then we need to check for the interaction and multicollinearity. Interaction is the pairing, the pair just now, the interaction term that we will check one by one, okay, to see if there is any interaction or not. So if there is any interaction, you need to include the interaction term in the MLR and run again the analysis. And multicollinearity is, we will check on the value of the VIF to make sure that it is less than 10. After we have checked the interaction done, the multicollinearity done, and then we need to check for the assumption, which consists of the normality of the residuals, and then residuals with the numerical independent variable, and then we check for the equal variance of the residuals and all, and as well as the outlier when we standardize the equation. Next, after everything is completed, then only we can present the data. So how to present the data is basically we will interpret, what we will interpret is we will look at the p-value mostly, okay, to see the association, okay, between the predictors and the outcome, as well as we will look at the adjusted beta. This is the regression coefficient, okay? Because based on the adjusted regression coefficient or adjusted B, then only we can interpret how is the regression goes, right? How is it goes? For example, here in the final model of using stepwise selection, there are 2 variables included in the model. We have mother's weight and we have smoking. So how to interpret these variables, mother's weight and smoking? It is based on the adjusted beta. Because in the equation, in the regression coefficient, we can determine if we increase 1x. Okay, 1x means the independent variable. If we increase in 1x, 1 unit of x, the unit can be anything, can be kg, can be centimeter, can be millimole per liter, for example. 1 unit increase in x will increase in how many unit? Okay, so it depends on the adjusted beta, right? This is how we interpret the connection or the regression, predict the regression based on x. All right, so at the end, okay, if you do MLR, basically we would like to see how would you interpret the adjusted beta. Okay, how would you explain the change of your dependent variable based on the independent variable? Okay. Am I answering your question? All right. So before we end our session, if let's say you have any questions, or you want validation, or you want confirmation of what you do, you can always consult us. We have a team. We are all statisticians, so basically you can just contact us. Okay, there is phone number here. Do contact us, and inshallah we're going to help you. All right, because sometimes basically from the experience of dealing with lots of clients and students and everything, sometimes they know the analysis basically, yeah, because everyone can search for it. Everyone can search for it. So basically, they just need validation or confirmation whether what they do, is it correct or incorrect, or some adjustment need to be done and things like that. So yeah, feel free to contact us if you want any assistance or help. Okay, any more question? All right, so if there is no question, I think that's all my sharing session for today. All right, hopefully, hopefully my sharing today met your expectation at the beginning of our workshop today, and hopefully you can apply whatever that you have learned today. And if you have any question, you can always contact me. All right. Thank you so much, everyone, for your kind attention, for the questions, and everything. Okay.
Thank you, Doctor.
Back to you, Sister Jihan. Anything else?
Thank you very much, Dr. Noor Ain,
Yes.
for an engaging informative session. On behalf of CPS, I am Quentin, and we would like to express our sincere appreciation for your sharing your knowledge and expertise with us today. And for all participants, thank you for your active participation and thoughtful questions. And also, we would like to remind you to fill the form for attendance and also the feedback. And with your feedback, we can improve the future programs. And with this, we have come to an end to our workshop today. And thank you and have a